Every bag of potato chips you open is the final result of an invisible chain that begins far from the packaging lines. It begins in the soil. Over the next 5 episodes, we will take you inside a state-of-the-art potato chip manufacturing facility. We will follow, step by step, the transformation of a raw tuber into one of the world's most popular snacks. It all starts here. These fields, typically located in regions with rich, well-drained soil and a temperate climate, supply the specific varieties bred for industrial chip production. Russet Burbank, Atlantic, Innovator, Lady Rosetta, Marquise, and others. These cultivars are chosen for their high dry matter content, usually above 20%, and very low levels of reducing sugars, 2 critical factors that ensure even color and crisp texture after frying. Potatoes arrive at the plant in multi-ton truckloads. Upon entry, rigorous quality control begins. Statistical sampling checks average size, specific gravity, reducing sugar levels, and the absence of serious defects or disease. Any load that fails is rejected outright. Tabbed potatoes then pass through next-generation optical sorters. Multispectral cameras, visible, near-infrared, and sometimes ultraviolet, analyze each tuber at rates of thousands per minute. Abnormal color, bruising, rot, sprouting, or foreign material triggers immediate rejection by high-speed air jets. This step achieves near-perfect purity before washing even begins. Next comes washing. The tubers are submerged in large, recirculating wash tanks where continuously filtered and disinfected water flows. High-speed cylindrical brushes scrub away soil, organic residue, and any remaining field-applied residues. The water is treated with UV or ozone, then reused at over 90% efficiency, an important sustainability measure in modern facilities. Once cleaned, the potatoes enter the peeling stage. The dominant industrial method remains mechanical abrasion. Whole tubers are fed into large horizontal drums whose inner walls are lined with coarse abrasive material. As the drum rotates, friction between the potatoes and the abrasive surface, combined with mutual rubbing, removes the skin in just seconds. Continuous water injection flushes the peel away, where it is separated, collected, and valorized, most often converted into biogas, animal feed, or organic fertilizer. At the discharge, the potatoes emerge smooth, uniformly white, and ready for slicing. At this point, the tuber has already undergone its first major industrial transformation. It has left the field and entered a world of extreme precision. In the next episode, we will witness one of the most visually striking steps, slicing the potatoes into thin, perfectly uniform wafers, ready for frying. The peeled potatoes, now smooth and uniform, enter the most critical phase for final texture, slicing. In a modern chip plant, this is no longer a manual task but a high-precision industrial operation executed at extraordinary speed. The tubers are guided, either singly or in small groups, into high-capacity centrifugal or multi-blade rotary slicers, frequently manufactured by Urschel or Heaton Control. These machines slice hundreds of potatoes per second. The blades, ground to tolerances of a few microns, produce wafers with thicknesses ranging from 1.0 to 2.0 millimeters, depending on the target product. Thinner for classic ultra-crisp chips, slightly thicker for ridged or kettle-style varieties. Laser or vision-guided automatic adjustment systems continuously fine-tune blade angle, feed pressure, and rotational speed. Any deviation exceeding 0.1 millicars is corrected in real time. Uniform thickness is non-negotiable. Uneven slices would fry inconsistently, resulting in burnt edges or soft centers. Immediately after slicing, the wafers enter a cold water rinse stage. High-pressure jets and air-agitated baths remove free surface starch released during cutting. Residual surface starch would cause slices to stick together during frying or promote excessive branning through the Maillard reaction. In advanced lines, rinsing occurs in countercurrent flow. Fresh water enters at the discharge end, while slices move in the opposite direction, maximizing cleaning efficiency while minimizing overall water consumption. Next follows a key thermal pre-treatment blanching. The slices pass through a continuous hot water blancher, maintained between 70 and 90 degrees C for 30 seconds to 3 minutes, depending on variety and desired outcome. This brief heat treatment inactivates polyphenol oxidase enzymes responsible for enzymatic browning, reduces surface-reducing sugars that cause dark frying coloration, and slightly softens cell structure to improve moisture evaporation during the subsequent frying stage. Some processes incorporate a small quantity of natural food-grade acid, citric, or ascorbic, to further stabilize color temperature probes and inline sugar analyzers ensure repeatable results batch after batch. Upon exiting the blancher, the slices remain saturated. A surface dewatering system, vibrating screens, centrifugal dryers, or high-velocity air knives quickly removes excess water, reducing surface moisture to below 5%. This step prevents dangerous oil splatter in the fryer, limits thermal degradation of frying oil, and prepares the wafers optimally for the cooking phase. The thin potato slices have now achieved the uniformity and conditioning required to withstand the intense heat of frying. In the next episode, we enter the beating heart of the plant, continuous frying, where the signature crispness is born. We now reach the decisive stage, the one where true crispness is created: frying. In a modern potato chip manufacturing facility, this phase relies on large-scale continuous fryers, the true thermal engines of the production line. The pre-treated and surface-dried slices enter the fryer in a continuous flow. They are laid in a single layer on a fine stainless steel mesh conveyor that slowly carries them through a bath of hot vegetable oil, typically maintained between 165 and 180 degrees C. The oil, most often a high-stability refined blend of sunflower, canola, or fractionated palm oil, is selected for its excellent heat stability and smoke point above 220 degrees C. External heat exchangers powered by gas, steam, or thermal fluid keep the temperature steady, with variations of less than ±1 degrees C across the entire length of the fryer. Upon contact with the hot oil, the internal water content of the slices, still approximately 70–80% of their weight, evaporates rapidly. This explosive dehydration produces the characteristic bubbles and causes the chips to puff slightly, delivering the light, airy crispness consumers expect. Residence time in the oil is brief, between 90 seconds and 3 minutes, depending on slice thickness and the desired product profile. Mechanical paddles or oil jet systems, such as OptiFlow or chip stir technology, gently agitate the slices to ensure even cooking, prevent clumping, and control whether the final chips exhibit a uniform curve or remain flat, as specified. Oil management is critical. Every minute, the entire volume of oil in the fryer passes through a continuous filtration system that removes fines, crumbs, and oxidized compounds. Rotary or centrifugal filters, combined with settling tanks, maintain extremely low levels of impurities, significantly extending oil life and preserving final product quality. Inline sensors monitor and automatically adjust fresh oil inflow and the delta T, the temperature drop caused by massive evaporation, by injecting hot oil at multiple precisely located points along the fryer. This programmable temperature profile allows the same line to produce classic chips as well as harder, crunchier, or lighter varieties. To meet growing demand for lower-fat products, some lines incorporate baking or hot air cooking alternatives. In these systems, slices receive a minimal oil spray, often less than 20% of final weight, before being exposed to high-velocity hot air at approximately 180–200 degrees C. While the texture differs from traditional frying, this method substantially reduces fat content while still delivering an acceptable level of crispness. As they exit the fryer, the chips have lost more than 60% of their original weight in water and acquired their characteristic golden color, firm texture, and the beginnings of complex flavor from the Maillard reaction. They are still hot, fragile, and full of potential. The next step will give them their definitive taste identity. In the following episode, we will explore the precise art of seasoning and the controlled cooling that finalizes the product. Fresh from the fryer, the chips remain hot, typically 80 to 90 degrees Celsius, and carry a thin film of residual oil on their surface. This exact moment marks the final sensory transformation: seasoning. In a modern manufacturing facility, seasoning is no longer a simple sprinkling, but a highly controlled, uniform, and measurable application that defines the product's taste identity. The warm chips are conveyed via elevator or vibratory feeder into a rotating seasoning drum, often referred to as a tumble drum or enrobing drum. This inclined stainless steel cylinder rotates at a controlled speed, typically 8 to 15 revolutions per minute, ensuring constant but gentle mixing. Internal flights or paddles promote even tumbling without damaging the fragile chips. As the chips move through the drum, a precision dosing system, vibratory feeder, auger, or mass flow controller delivers the seasoning blend. Flake salt, barbecue powder, cheese flavor, vinegar notes, herbs, exotic spices, or multi-component formulations. Dosage is tightly regulated, usually between 1% and 3% of chip weight, in full compliance with sodium and labeling regulations. The residual heat from the chips causes the surface oil to become slightly tacky, allowing the powder to adhere uniformly without requiring additional oil in most recipes. For more complex or moisture-sensitive flavors, a fine mist of flavored oil or emulsion may first be atomized onto the chips. In the most advanced systems, electrostatic seasoning technology enhances efficiency and uniformity. The chips are given a positive charge within a grounded drum, while the seasoning particles are negatively ionized via a high-voltage bar. This electrostatic attraction draws the powder directly onto the chip surfaces, achieving up to 98% coverage with 10 to 45% less seasoning material, thereby reducing waste, airborne dust, and production costs. Inline optical sensors or multispectral cameras continuously monitor coating uniformity. Any deviation, over-seasoned patches, or bare spots triggers automatic adjustment of feed rate or generates an operator alert. Immediately after seasoning, the chips enter the controlled cooling phase. They pass through an air impingement tunnel, fluidized bed cooler, or high-velocity ambient air system where filtered air, maintained at 15 to 25 degrees Celsius, rapidly reduces their temperature to near ambient levels in 2 to 5 minutes. This quick cooling locks in the flavor volatiles, prevents moisture condensation that would compromise crispness, stabilizes texture, and minimizes oil migration prior to packaging. Exhaust systems capture residual seasoning dust, maintaining a clean production environment. At this stage, the chips have acquired their complete flavor profile. Crisp, flavorful, and consistent. They are now ready for the final journey from the production line to the consumer. In the concluding episode, we will follow the path through packaging, final quality assurance, and global distribution. We now reach the concluding stage, the one that transforms freshly seasoned chips into a shelf-ready consumer product. In a modern facility, packaging is a highly synchronized operation that combines speed, hygiene, product protection, and traceability at an industrial scale. The cooled, seasoned chips arrive at a multi-head electronic weigher. This system distributes the product into exact portions, commonly 1 oz, 1.5 oz, 5 oz, or 10 oz, with tolerances typically below ±1.5%. Each bucket releases its precise charge into a funnel that feeds a vertical form fill seal machine. A roll of multi-layer plastic film, frequently metallized polypropylene or PET aluminum PET laminate, is unwound, formed into a tube around a forming collar, and sealed longitudinally with a heat seal bar. The chips drop into the formed tube horizontal sealing jaws, then close both the top of the previous bag and the bottom of the next bag simultaneously, while a knife cuts the packages apart. This cycle repeats at rates of 80 to 15 bags per minute, depending on size and format. But more durhu. Immediately before the final top seal, a food-grade nitrogen flushing system displaces oxygen from the headspace. Nitrogen levels are reduced to below 2%, dramatically slowing fat oxidation and maintaining crispness throughout shelf life. Some lines apply a controlled nitrogen-oxygen blend or slight vacuum depending on the product specification. The hermetic seal ensures long-term stability, typically several months, at ambient temperature. Every sealed bag immediately undergoes rigorous automated quality assurance. First, a high-sensitivity metal detector scans for ferrous and non-ferrous contaminants down to 0.51 millibrit in size. Next, an X-ray inspection system examines the entire package contents, detecting dense foreign bodies such as mineral fragments, dense plastics, glass, or bone, even if hidden within the product mass. Finally, industrial vision cameras verify external appearance, seal integrity, print alignment, barcode legibility, and film condition. Any non-conforming package is automatically diverted by a pneumatic reject arm to a quarantine lane. In addition, statistical samples are periodically pulled for sensory evaluation, physicochemical testing, salt content, moisture, oil acidity, and microbiological analysis in an on-site laboratory. Accepted bags are collated into corrugated cartons, typically 12, 24, or 48 units, by case packing equipment. These cartons proceed to robotic palletizers that arrange them in optimized, interlocking patterns for maximum stability during transport. The completed pallet is automatically stretch-wrapped, banded if required, and labeled with RFID tags or 2D barcodes that enable real-time traceability throughout the supply chain. Within hours of leaving the fryer, the chips depart the facility on temperature-controlled trucks bound for regional distribution centers, retail warehouses, or international export points. And so concludes the industrial journey of a simple potato. From meticulous variety selection in the fields to protective packaging under modified atmosphere, every stage has been engineered for consistent quality, food safety, production efficiency, and increasing environmental responsibility. Join the channel to access more authoritative industrial insights.